Have you ever really thought about the water in your glass? I mean, it just sits there, right? Looks pretty simple. But hiding just beneath the surface and deep within its molecules are some absolutely incredible forces. We're talking forces strong enough to let insects walk on water and powerful enough to literally tear apart solid steel. Okay, let's dive into this hidden world.
You've seen this stuff a million times. A little water strider just gliding across a pond like it's solid ground. Or that slow, agonizing ooze of honey when you're trying to make tea. Well, these aren't just little quirks of nature. Nope, they're actually demonstrations of some serious physics hiding in plain sight. So, let's pull back the curtain and see what's really going on.
All right, here's the game plan. We're going to start by looking at that delicate skin on water that acts like a trampoline for bugs. Then we'll get into the internal friction that makes honey so slow. After that, we'll see how these forces can actually make liquids defy gravity. And to finish things off, we're going to uncover the surprisingly destructive power lurking inside a tiny, simple bubble.
First up, surface tension. Now, the best way to think about this is to picture a thin, invisible, kinda stretchy sheet pulled tight over the surface of any liquid. It's the whole reason water beats up on your car, and it's why you can, very carefully, float and needle on water. So what is it really? Well, surface tension is basically a force that pulls all the molecules on the surface of a liquid inward, making them huddle together. It forces that surface layer to act like a flexible membrane. And this force is always trying to shrink the surface area as much as possible, which is exactly why a free-falling raindrop pulls itself into an almost perfect sphere. And all of this comes down to a constant battle between two different forces. On one side, you've got cohesive forces. That's the attraction between molecules that are the same, water sticking to water. This is what creates that elastic skin. But on the other side, you have adhesive forces. That's the attraction between different molecules, like water sticking to a pane of glass. This is what causes things to get wet. And the tug-of-war between these two is going to explain almost everything else we talk about.
A simple soap bubble is actually a perfect lab for this. See, it's not just one surface. It's a super thin film of water sandwiched between two layers of soap. That means you've got surface tension on the outside surface pulling in, and you've got surface tension on the inside surface also pulling in. You've essentially got double the force working here.
And the key thing to remember is that this force is totally real and totally measurable. If you took a 40mm soap bubble, that doubled up surface tension creates an internal pressure that's 2.5 newtons per square meter higher than the atmospheric pressure outside. Now that might not sound like a huge number, but think about this. That entire pressure difference is generated just by molecules pulling on each other. It's pure molecular attraction doing all that work.
All right, so those cohesive forces we just talked about, the way molecules like to cling together, they create another property you're definitely familiar with, viscosity. If you've ever tried to pour cold maple syrup, you already have an intuitive grasp of what this is. Viscosity is just a fluid's resistance to flowing. It's basically internal friction. But what's really interesting is that viscosity works completely differently in gases versus liquids. In gases, it's all about molecules bumping into each other. So when you heat a gas, the molecules fly around faster, they collide more often, and so the viscosity actually increases. But in liquids, it's all about those sticky cohesive forces. When you heat up a liquid, those forces get weaker, the molecules can slide past each other more easily, and the viscosity decreases. It's why hot oil flows so much better than cold oil.
Let's just walk through that. Imagine you're heating up a pot of honey. First, the temperature rises. That extra energy starts to loosen up those cohesive bonds that are holding the molecules together. Since they aren't clinging to each other as tightly, the molecules can now slide right past one another with a lot less effort. And boom, the overall viscosity just drops.
Okay, so we've seen how forces inside a liquid create a skin and cause friction. But when these forces interact with a surface, they can do something that looks impossible. They can actually defy gravity. This phenomenon is called capillarity, and it's how a giant sequoia tree pulls water from the ground all the way up to its highest leaves.
To put it simply, capillarity is just the ability of a liquid to flow in really narrow spaces, sometimes straight up, against gravity. And, you probably guessed it, this is another direct result of that battle we talked about, between cohesion, where molecules stick to themselves, and adhesion, where they stick to other things.
It really all comes down to which force wins the fight. For a liquid like water in a glass tube, adhesion is stronger. The water molecules are more attracted to the glass than they are to each other. So what happens? The water literally starts climbing the walls of the tube. But for mercury, it's the exact opposite. Its cohesive forces are incredibly strong. Mercury loves sticking to itself, so it actually pulls away from the glass walls, causing the surface level inside the tube to drop.
And this effect can be pretty dramatic. If you take a thin glass tube, only about 2.5 millimeters in diameter, that's about the thickness of a nickel, water will actually climb an incredible 11.8 millimeters up the tube, high above the surrounding water level. That is a powerful upward pull, driven by nothing more than molecules sticking to glass. But put mercury in that exact same tube, and it does the complete opposite. Because its own molecules are so tightly bound together, it pulls away from the glass. It actually gets pushed down, creating a dip of 4 millimeters below the general surface level. Seeing these two side by side really shows you that epic battle between adhesion and cohesion in action.
So for our last topic, we're going to pivot a little bit from these curious phenomena to a genuinely destructive force. It's called cavitation, and it all starts with something that looks as harmless as a tiny bubble forming in a liquid.
The whole secret to this is a concept called vapor pressure. Now, we all learned that water boils at 100 degrees Celsius, but that's only true at sea level air pressure. The trick is, if you lower the pressure around a liquid enough, it will start to boil and turn into a gas or vapor even at room temperature. And that right there is the trigger for cavitation.
So here's how it plays out. In a really fast-moving fluid system, like the water swirling around a ship's propeller, the pressure can drop so low, so fast, that the liquid instantly boils and forms tiny vapor bubbles. These bubbles then get swept along with the flow into an area where the pressure is higher again. The higher pressure immediately squeezes the bubbles from all sides, and they don't just pop, they collapse violently. They implode, releasing a massive amount of energy in a tiny, focused shockwave. And that energy is unbelievably destructive. I mean, imagine millions of these little bubbles imploding every single second. Each collapse acts like a microscopic jackhammer, just blasting away at a metal surface. Over time, this constant assault pits and erodes solid metal. This is a huge, huge problem for ship propellers, for the impellers inside water pumps, for hydraulic turbines. It causes major damage, a ton of noise, and a serious loss of efficiency. It's just a wild reminder of the immense power hidden inside even the simplest fluids.
So, from the delicate skin of water to the sticky friction of honey, all the way to the destructive force of a collapsing bubble, it's clear that even the simplest liquids are run by this complex and powerful set of invisible rules. Kind of makes you wonder, doesn't it? What other amazing forces are out there shaping our world, hiding in plain sight,